So this is the first slide, where and this is a work done with Yanis Ballars in the University of Latvia, where I am at the moment, working with him for a few months, very complicated with COVID. But there was a lot of work previously, which also will be in the presentation with Yusuke Doi and Masayuki Kimura about breathers with wings. Pardon? And also with Jaroslav Slotariuk from there, a bit, and Yurko Sevis from Moscow about kings, about experiments with hyperconductivity with microrossals. I'll talk a little bit about them, but very little. And many simulations were done previously with Yanis Ballars and Chris Helbig. And very important, Masayuki Sato, which we talk about the spectral theory over sushi. And that was the beginning of this line of research. And let's do a small detour. I think it's appropriate to remember also my work with IDDA. We wrote 7 publications. The first ones also a few ones with Peter Christiansen, also here, and Yuri IDDA, also I think originally from Ukraine. This work with IDDA was so important in my career, and also with Peter Christiansen. We started working about DNA and proteins and these kind of models and dipolar interaction. And the last one was also about that subject, although a different approach. And actually it was proposed or started when a meeting I organized in Kiev. Here you can see Yuri IDDA. University in Altea, a beautiful city in Spain, and Larissa. We also see Bakohar and a few other friends like Chris Helbig and Magnus Johansson, and Chris Helbig's wife, and Jonathan Wattis. We had a very nice time there. Also, Lina IDDA was there. It was like a vacation and also work, and that work I started there. Also, before I was starting, the picture I chose from the starting slide is this beautiful picture of the Dnieper, which is the river, as you know very well, on Kiev, and I think the largest river in Ukraine. And there are 2 reasons for participating in this meeting. One, of course, is my collaboration and my memorial on Yuri IDDA and other colleagues and friends. But also because we are in this very difficult situation for Ukraine and our Ukrainian friends. And I thought of participating was a way of showing them that we think of them, that we are worried, not as much worried as them, for sure. We are worried about this difficult situation, and we expect that everything will be eased and there will be, of course, peace, but also tranquility, and people could just follow on with their life. Yes, I think it was important to show that many people are outside Ukraine, are very worried and very express our solidarity with our Ukrainian friends and colleagues.
Thank you very much, Juan.
So, thank you, Larissa. So let's go back to my talk. And I added, which is not in just the word exact, because it's also important. And somehow I cannot see completely with this this bar. But anyway, so there are some questions about the title. Why we were interested in frequency, moment, or spectral representation? Why exact solutions, and why unexact hexagonal lattice? And I will comment very briefly about all of them before starting. And the reason for spectra is because we sometimes will have physical spectrum, and maybe we can see breathers. For example, we have in this picture of a neutron spectroscopy of lead selenium, lead selenite by Mali, and there are a lot of bands here. And is there maybe some breathers here? How we could recognize them? So that's a very important thing to know. But also, spectral representation will be very useful to find what is in a simulation, to see just a cup of an eye, what is there, and to find also many parameters just looking at the spectral or the Fourier transform of the simulation. Why exact? Why exact breathers? Because exact breathers will repeat forever their exact solutions, so they will have an infinite life theoretically. Even, of course, even in numerical simulation, there will be some rounding error, or maybe at the end they will not. We can understand very much better the properties because they are actual solutions. We could expect that other last living solutions, traveling solutions, will be approximates and they tend to them. And there is an inconvenient that maybe we don't like exact solutions, and that's very often the case, because very often exact solutions will have wings, not tails. Tails is this like the decreasing amplitude at the borders of the core of some solitary wave, but wings are just stand forever in our whole system with tending to a constant amplitude, and so we don't like them because they are not localized. That is actually a very generic solution, but then very often is the case that we have to choose. We have an approximate solution which is localized, or a exact solution which is not completely localized. And this paper by Boyd says this phrase, this sentence, his opinion, and they find that sentence is the Kane solitons are just the most prominent part of the debris. I think this means that he didn't like that debris of an initial value solution. So yeah, we have wings, but if we have wings, we have an exact solution. We can also use path continuation and then go to find that maybe some values of velocities or frequencies will find small wings and maybe they will disappear. And that's often also the case, that they will disappear for some specific values of the parameters of the velocities, some discrete set of parameters. Why hexagonal? Because this is the structure of many layer silicates of the mica group. And these silicates are important because they're for us, because there is fossil evidence. There are those tracks that appear that are caused by localized excitations in the fossil record. And in the most recent review of this subject is here in this chapter. But also there was experimental evidence of nonlinear excitations in this work by Russell and Eilvik. We sent alpha particles on a piece of muscovite, and then they will observe the ejection of an atom along the closed path directions at the other side. And Russell and myself, we also arrived at the conclusion that some those nonlinear excitations have charge, and do experiments showing what we call hyperconductivity. And it is that the alpha particles produce nonlinear waves, and we observe charge transport, but without an electric field and at room temperature. Also, there are very good simulations by Bayard and collaborators, and of course it is 2D, which is much simpler than 1D. So here we have in this model of atoms, this will be the potassium atoms, actually ions, who are subjected to on-site potassium due to the layers above and below. And we can see the hexagonal lattice here in this 2D picture. So in the model we'll use, actually there are a couple models we'll use, but similar. I want in those details now. So they will have kinetic energy and on-site potential, which is a frontal control potential, the simplest thing we can usually think of a periodic potential, and also Leonardian potential for interaction potential. It can be done for one neighbor or several neighbors. Some details about how to smooth it, but I'm not also to enter that. So here I have a picture of the substrate potential in 2 dimensions, and here we have the reciprocal, sorry, the direct lattice unit cell of the contour plot of the on-site potential reveals this structure, and our breathers will travel in this direction, in closed path direction along the x-axis, and also, of course, could be any equivalent direction. I also can have time to enter in more details, but then this is the contour plot of the phonon bands. There are two because we have two variables, x perturbation in x and y, and it's interesting and have some consequences that our breathers will propagate in this direction, which is not one of the direction of the primitive basis of the reciprocal space. And this gamma is centered to k will be the preferred direction. And here we have the phonon spectrum in that direction. It's interesting to see that here we have this maximum. Here will be produced though our breathers near the top of this band, and this band has interesting polarization, that it is that there is no vibration in the y direction, only in the x direction, which I'm sure helps a lot to the stability of the breathers we have found. So let's go to WK representation, and this is a stationary breather. We will be just in this part from here to here. And stationary breathers, they have a single frequency or maybe also harmonics, but mainly a single frequency. They will be centered for hard potentials near Q equal to pi. And here also we have a stationary soliton of King. How this picture changes when it is we have a moving breather or a moving solitary wave in general. So we will have this sample of a simulation. We will have that band becomes tilted. So we have like this approximately, this is not exact. We can see that there are some frequencies here on the phonons or close to the phonon band. And so main thing is that the moving breather appears as a band. This is a band. It doesn't have a single frequency, but it is mostly about this line. This is actually continuation at that other side. And there are maybe also some interaction with the phonons or close to the phonons, which we call the wings. A very important thing is that the frequencies of the breather, they don't have to be above the phonon band. They have to be for the same Q at some frequency of the breather, because they have very many. The corresponding frequency of the breather, will be above the frequency of the phonons with the same momentum, but not in general. So that's a very important property. So this is a generic solution. We have actually these wings. We'll see very soon about them. These wings, and they extend forever. And this staggered profile, which means it is very close to wave number of pi, but of course there is not a single wave number. There are very many, but there are is a dominant one really close to that. So let's define exact traveling waves. And then there are two important concepts that are, I think this probably is not new, but it was a bit not difficult to find, at least in a very easy way. And so there are two concepts which are fundamental time and step. And a solitary wave will have the property that it repeats exactly after this time, which we call the fundamental time, but a different position displays what you call the step, an integer number of sides, the step. That is the property of a solitary wave. That's as sure that we have in this repetition, exact repetition. And then this defines the fundamental frequency, 2pi divided by the fundamental time. This will be a very important frequency because everything will be integer multiple, or almost everything will be integer multiple of this fundamental frequency. And the velocity is very easily related with these two these values, just the step divided by that frequency. So here we have some example. We have in this case this breather, who is in this black board here, the particle. After the fundamental step, after the fundamental time, it moves 2 positions, and it is exactly here. Sorry. Again, we have it here. there is also all the other ones. There are, of course, other frequencies in the system, and we'll see some of them, but just concentrate in one of them. We have a very important time, which is the time to travel a lattice unit, and its frequency, which is just in one as the, and the lattice unit will be 1 divided by the velocity. And this have the consequences that the frequency will be integer times the frequency velocity, or integer times exactly the step times the fundamental frequency. So how we describe, we started first in one dimension. How we describe a solitary wave then will be a function with, or a sum of function of this shape of this first variable will be localized in this first variable, and 2 pi periodic in this one. So this frequency here will be yes, actually, if we're moving with the brother, this term will be 0. It means this frequency here, double y, it is actually in the frequency in the moving frame. So we will have, if this frequency is 0, we'll have soliton or a king. So the condition for the exact breather is very easy to apply, and then the consequences is frequencies, or typically just one or very few, are integer multiples of the fundamental frequency. The general form will be this way, or these multiple frequencies of the fundamental frequency, but typically we have just very few, 1 or 2 or 3. So the thing is that if a traveling wave has that structure and that property, we know that we can have a basis which is the plane waves, but actually for a traveling wave of some specific velocity, we will have a subset, a basis which is a subset, and it is the plane waves that also have the same property, that they are exact waves with the same velocity. And this means we can also put it in the same form that we saw for the traveling waves, that is a term depending of n minus the velocity time, and then also here a moving frequency, which will be also an integer multiple of the fundamental frequency. So this means that the laboratory frequency, which is the one we have up here, will be a line with respect slope and velocity with respect to q, the momentum, and in these terms here will be the frequencies in the moving frames at the q equals 0, and they will be then the integer multiples of the fundamental frequency. So if it's easier to see in a picture, so we will have that all the frequencies of the traveling wave will be in those lines, parallel lines, and the cutting point with those parallel lines of these lines is in the moving breather frequency. And also we may have these cutting points with the foreign band, and those will produce the wings, Here is sometimes important, the pi frequency or the rest frequency, because it is one of the many frequencies possible for in the breather line, but the one that typically we use to produce a stationary breather. Then we will have many more frequencies, but that is very often the frequency of the stationary breather, the pi frequency, that we will perturb to produce a moving breather. And this is an actual representation of a simulation. This is probably better to see it in 0-2. We have in these intensities here of the Fourier transform. Here have the wings, and here is the corresponding picture. So basically we have seen these properties already, only that this the rest frequency that the very much is used for is actually maybe an integer, a semi-integer multiple of the fundamental frequency if the step is odd. It's not from the point of the breather, we are used to it, but it is not so important, so it doesn't. But it is often that the case. Yes. Sometimes it's easier to see all those properties in the moving frame, and so the dispersion relation changes. And now we have, if we represent here the moving, the all the frequencies that will be in the moving frame divided by the fundamental frequency. Just we will have as integer values, we have the possible frequencies. And here we have the breather, and here we have the pin. Yes. For short potentials, these things are actually easier because this the moving breather frequency is again this cut here, that it is below this minimum, and it's also in the instead of the pi frequency, the ref frequency will be the 0 frequency. For kings, they have the moving frame frequency 0, so they will cut in the 0 here. Also, we may have wings here. So how this change when we go to 2 dimensions, and then we have, of course, 2 variables which correspond to indexes of the sum of the Bravais lattice, but maybe a sublattice of the Bravais lattice, also Bravais lattice. And we will have localization in principle in these 2 variables, although we may have some standard wave kings with only localization in one of them. And also these frequencies here, this variable here will be, the function will be 2 pi periodic in it. And again, this WY will be the integral multiples of the fundamental frequency. No change. No change. So instead of having now resonant lines, we will have some surfaces of K1, K2, the parameters, the coordinates in the reciprocal lattice, and one of them, the one corresponding to the propagation of the solitary wave, we have that the derivative is with respect to that variable is the velocity of the solitary wave, and the other is 0. There is no propagation in that direction. This means that we will have actually planes. We will have planes that are parallel to that coordinate A2, so that's the basis A2, and then with this angle BB. So if we apply it to our model, where we have found these exact breathers propagating, here we have just one of them. In 2D, here we have just equal intervals, I think it's 20 fundamental times. We have these 3 snapshots of the breather to see how well it propagates. And if we look first at the central line where it's propagating, we have this Fourier spectrum, and we can see here the breather, but also we can see here that there is also a soliton. There are both things at the same time. Both things at the same time have a soliton breather. And we can see the different amplitudes here. It says soliton is smaller, amplitude is smaller too. And here it is. There are possibly more things than more, but we cannot see them. There are actually wings cannot be seen. And so this is the picture of the variables. In this soliton is constructed, filtering out the higher frequencies and then doing the inverse Fourier transform. And here we can see how the soliton is moving and the breather, actual breather plus soliton, same there together. And of course, it's very easy to see this property in the Fourier spectrum, in the spectral representation. Not so easy initially in that place. So from that, we can find what is the fundamental time, because we will have, depending which is the step, we'll have several possibilities, and just looking at the coordinates, we can decide which is the fundamental, which is the step, and then the fundamental time. If we do now the projection of the Fourier transform in 2 dimensions, two spatial dimensions, or 2 reciprocal space directions and frequency, then we have that there are other lines here, other bands, and these other bands becomes very clear. Well, we'll go in a minute to them. So here we identify them very easily. But everything here is the resonant lines. This will be the brother frequency, and here we can see from 0 that it is the fundamental frequency. we can, the thing is that in 2 dimensions we have now here we have here pictured the whole 2-dimensional spectrum of the phonons, and we can see that those new lines that appear not new intensities correspond to other phonons which are in that surface. The picture becomes actually most clear, but when we do see it actually in dimensions, and then we have seen here that the planes that are substitute the resonant lines. We have resonant planes. This plane corresponds to a single frequency in the moving frame. We have all those intensities here, and basically cover all the reciprocal lattice because the localization is so good that it's basically 1, and so the spectrum Q covers all the reciprocal lattice direction. Here we have the phonon surfaces, and we have here intersections where the winds may appear. It doesn't mean that they are all appears in all intersections. That depends on the system, but will appear here in those intersections. And here we have also the band corresponding to the soliton. A very not conventional representation is that we also can do the Fourier transform only in the variables of the propagation x and t, and leave the order coordinates n, y, and then we can see very well the extraordinary localization of these waves here. It's more maybe nicer to see here in this way that in those planes there.
Juan, so, how many minutes do you need? Because you are out of time already.
Am I? No, I have 3 minutes.
Yes.
Right?
Oh, 3 minutes. Okay.
Yes.
So then, just to remind you.
Until yes. So how to happen if we come back in 3 dimensions for a real spectrum? Then what will happen? Instead of this breather band, we have different ones because we have breathers in principle. We can have different velocities. So we have some breathers here, some others here. They will be not as well localized as the ones we have in our simulations. And of course, instead of this line here, we'll have a 3-dimensional, something like a valley here. And we will have breathers in all possible directions. So we'll have something like a bowl. We have something like a bowl here, and it will be thicker, and this is a picture of the bowl. It will be thicker. The exact form, it depends on the system, but something like this. Well, that is more or less what we have in this Newton spectrum here. And it's not, at least this is the acoustic band, is the optical band. So we have this thing that seems very much similar to that. Although we cannot guarantee exactly that they are moving together, there is actually a big possibility in this paper they are located at harmonic excitations. So this is all. Conclusions I already have said during the talk. And the main one maybe is that in the reciprocal space, the solitary waves are very well defined, very well described, and very easy to see what is happening there, and not so easily with the normal coordinates. And of course, it's what we need if we want to find them in the spectroscopy. So thank you very much, and that's all for the moment. These are these papers related with this talk, but basically I'm finished.
Thanks a lot for a very nice talk, and yeah, you're almost in time. So please, questions if you have. Does anyone have a question? Please raise your hands.
Can I ask a question?
Yeah, please go ahead.
Juan, thank you very much for very interesting talk, and it was really exciting. As Yuri Gadiday often used to say, to understand on fingers. Do I understand correctly that in your phonon spectrum there are 2 bands, acoustic, 2 branches, acoustic and optical? And I have a feeling that a soliton is formed because of the interaction mainly with the acoustic band, while the breather, or thank you very much for this term, breather, I like it very much, is formed mainly by the interaction with optical phonons, and therefore it is split below the phonon band. And what type of boundary conditions did you use in your numerical experiments? It looks like you had periodic boundary conditions.
Well, we have yes, periodic condition, of course. That's an important point. I cannot see who I'm talking with.
Larissa Brzyk.
Larissa. Yes, the two bands, they are not really well described as optical and acoustical, because of both of them, the system is a bit special because we have this on-site potential. That means there is no acoustical band. There is no band that goes to zero. So both bands are optical, and the difference between them is the polarization, because we have two variables, displacements in X and in Y, and the difference in those bands is the polarization. In the extreme cases, we have only vibration in the X direction, and in the other extreme case, we have only vibrations in the Y direction. So it's not exactly these acoustic and optical properties.
Thank you very much.
More questions? I do not see any. I have a maybe naive question. Why it's so important to have a hexagonal crystal lattice? So if you go to square lattice, would the effects disappear? So do you need a kind of frustration, or it's simply easier to work with a hexagonal case?
Well, it's not easier, because easier, of course, will be a cubic lattice. So that's why, because we are interested in this kind of propagation in these models for the interlayer in the silicates of the mica group, and they have that hexagonal lattice. But I think there are some specifics of hexagonal lattice relating and where are the second neighbors, and relating with the reciprocal lattice structure that make it favorable for the propagation of solitary waves. But yes, the theory is not restricted to hexagonal lattice, neither to two dimensions, because as I commented in these ideas about how it could be, for three dimensions will be much more difficult to represent, but of course, and to see, but of course, they also will be, instead of, we'll have hyperplanes instead of planes, resonant hyperplanes, and their projections in 3D will be planes, but so it's all more difficult to see, of course, but in principle it's not limited to hexagonal nor to the lattices.
Thanks. And more questions? If not, please stop sharing.